Welcome to the last session of our little course, Machine Learning First Steps, which is going to include a CNN case study. The course was presented to you by Summer. So what are we going to do in this tutorial? We're going to apply CNN concepts on a gate mode recognition problem where we need to determine the exact gate phase for a locomotor, where we are going to, for example, design a robotic assistive device for that locomotor or for that person. So we need to design a high-level module that is able to determine the exact gate phase or gate mode of that person and predict what kind of assistance that person needs, or what kind of actuation is needed for the knees and ankles of that person. We're going to see for ourselves how powerful CNNs can get, and of course we're going to conclude our little machine learning journey. So let's go. So for this CNN code, we're supposed to deal with a problem. We are trying to classify the gate mode, or the current phase of motion that a locomotor is undergoing. So basically we have some classes like ramp ascent, ramp descent, ground level walking, sitting, standing, stair climbing, and stair descent. So basically we have like 7 different classes, which makes the problem very challenging. At the same time, we have a data set which includes some sensory readings, like IMU readings, or inertial measurement unit readings, attached to both, or having IMUs attached to both legs. And we also have some goniometers attached to some of the joints, like the knee and the foot, for example, or the knee and the ankle. So all of these are just fed through different channels because we have so many sensors, and we have timestamps for these sensors. So we have 2 dimensions. One of them is the time, where we basically try to divide the sensory feed into some windows, each of these windows having a time duration. For example, for this particular example, I think it was 0.05 seconds. And at the same time, we have another dimension, which is the number of sensors, or the label of that sensor. It might be a knee IMU, or a foot IMU, or an ankle goniometer, or a knee goniometer. So basically, I think we have 19 sensors attached to both legs. So we might think of that as an image, since it has 2 dimensions. An image which only has 1 matrix, instead of 3 matrices. So basically have like a grayscale image with 2 dimensions. One of them is time, and the other one is the sensor label. So we're going to write our code where this input is fed to a CNN. What I'm going to do first is I'm going to import the libraries that I need. I need NumPy and I need pandas. I might need some functionalities from math, like floor, which basically computes like rounds, which basically rounds up or rounds down a decimal. So if I have like a number like 2.6, for example, the result of a flooring operation would be 2. We also need TensorFlow and TensorFlow layers, or Keras layers. So we have some familiar functions here, like convert to 1 hot. We already went through that before, and convert from 1 hot as well. So there is a function called process here, which basically like analyzes the data, or the raw data set coming from a CSV file, and just converts this data into usable NumPy arrays. So you needn't concern yourself with this part, because this part doesn't have anything to do with the CNN itself. It's just like a pre-processing step. So what I need to focus on now is the model part. So we're going to use the functional API again in order to create a CNN. So first of all, I'm going to determine my input frame, and as we said before, we should pass the input shape as an argument. Then I'm going to include a couple of layers. First, we have a convolutional layer. So I'm going to use the conv2d function in order to implement or execute the convolutional part. So I'm having 10 different filters. So I'm going to use 10 filters. And each filter or each kernel will have a size of 3 by 3. So these are the first two input arguments. And then I'm having an activation function, which I'm going to use for this convolutional part. As we said before, I'm going to use a tang function for this. Some people might suggest ReLU, but tang just worked fine for this part. And I'm going to pass the input to this convolutional layer. Then I'm going to use a max pooling layer. So I'm going to use the max pooling 2D function. And the pool size, which determines like the kernel size of the pooling layer, is going to be 3 by 3. And I'm going to use a stride of 2 instead of the default stride 1, because I need to reduce the size of the input, like in terms of width and height. So it's better to use a stride of 2 because that would reduce the output size more than a stride of 1 would. And here I'm applying a padding or a type of padding called valid. All right. So I'm going to pass the Z1 layer here, which is the output of the convolutional layer, to this max pooling layer. And then I'm going to flatten all of this in order to start a fully connected partition. So I'm going to flatten the output of this max pooling layer using the flatten function. And then I'm going to start to include more fully connected layers. So I'm going to have a first layer, which is a very normal layer with 400 hidden units. And of course, this is of the type dense, because dense means like a fully connected layer or a normal layer. And I'm going to use a ReLU activation function for that part. Then I'm going to apply something called dropout. And basically, dropout is something that controls regularization. Well, it's a different regularization method other than penalizing weights. So I'm just, we don't have to go through the details of a dropout or how it works. I just included to reduce the gap between the training performance and the testing performance. So in order not to have a huge variance between the two, I'm just going to embed a dropout. So what a dropout does is it basically ignores some of the weights, or ignores some of the weights during the training process. So it trains less parameters per epoch, and it randomly ignores a particular set of weights for each training epoch. And this helps like train less parameters per epoch, which makes like the training process more biased towards some weight in a random fashion. And this helps regularize the output. We don't have to go through the exact details. We don't have to explain how that works really. I'm just adding this for decreasing the variance between the training and testing data sets. Then I'm going to include another dense layer, or another fully connected layer having 50 hidden units and a ReLU activation. then another dropout, and finally I'm going to have my output softmax layer. And since I'm having 7 classes, so I'm including 7 hidden units here. And basically that's it. I'm going to return the model once I create an instance of this model in my actual code. So here I'm determining my train list, which is a list of the CSV files I'm going to include for my training dataset, which is basically for a subject of 194 centimeters height, 194 centimeters grown up, adult, and this happens to be like data collected for different circuits of motion, where a subject or a test subject is supposed to perform some locomotion activities in an ordered fashion. So you're supposed to like sit first, then stand, then walk, then climb the stairs, and so on. So each of these circuits determines the exact order of motion, and he repeats, he or she repeats, I'm not really sure, but since this seems to be a pretty tall individual, so it's more likely to be a male. And then he repeats the same cycle over and over, so each of these circuits presents the same cycle, repeated again, for the same subject. And I'm picking one of these circuits or 2 of these circuits as my test subject because they haven't been used for the training. So if I'm able to classify the training or the locomotion activities pretty well for this test list, then that means I'm able to predict the locomotion activity of that person in any possible situation or any situation that I haven't seen before. Someone might argue that I've seen this cycle before, but the thing is, when I'm pre-processing my data set, I just shuffle the data, so the data, well, is not ordered. Then that means the activities are scattered now. So when I'm training my network, I'm actually feeding like different activities that are no longer ordered or arranged. So I might pass, for example, an example for walking, then an example for sitting, then an example for stair climbing. So they are no longer ordered. So the network has no way of telling what the order of the activity is. So that means if I include a locomotion activity or locomotion example that I haven't seen before, and I have no idea about what the past activities was like, or the past activity was like, then that means I'm able to extract the sensory information and just tell what this guy's doing right now without prior knowledge of any past activities. So that means that the test data still remains unseen. However, it might be slightly better if we include a different test subject as our testing dataset subject, because that would be truly unseen data, because that is someone I've never seen before, and I've never seen this circuit before as well. But it's hard to achieve a high accuracy with that. I mean, even in the literature, we cannot achieve like an accuracy more than 85% for unseen subjects. So here I prefer to deal with one subject. Let's assume that we're designing an active orthosis device for this particular subject, and we need to tune the device to his own walking pattern. So that means that the unseen circuits happen to be like proper testing dataset material. And for that, I'm going to include the circuits that I've not seen or not used for the training, while these are the circuits that I've used for the training. These are some settings for the data pre-processing. I'm not, well, I don't recommend reading them at all because pre-processing is like out of scope right now. We'll just assume that we have the data prepared, so you'll just include that part in your code. This data pre-processing step actually was included by me. And you don't have to concern yourself about it because it has to do with like the biomechanics of motion, so you don't have to care about it. Then I'm going to construct my dataset arrays, basically, which is the X train, the Y train, the X test, the Y test, as we did before. So basically, this is the outcome of the whole pre-processing step. Then I'm going to create an instance of my model here, and as usual, I'm going to pass the shape starting from the second dimension or the second axis, and just ignore the axis which determines the number of examples. And then I'm going to use the compile function, and I'm going to use this optimizer with a learning rate of 0.05 and the loss being categorical cross entropy, since we have more than one class, or just have like, we don't have like a binary classification problem, we have a multi-class classification problem here. And I'm going to include accuracy as a metric. And I'm going to type the summary of this model. And for the last step, I'm going to prepare the tensor slices of my, basically produce my tensor data sets or tensor dataset objects in order to fit my model. And I'm going to use the function fit in order to fit my model. Here I'm going to include a large number of epochs because CNNs usually take longer to train. They need a lot of epochs. And this actually might be very slow even for a device with a GPU, because I've been waiting for like 10 minutes for my network to train. So maybe on a device with just a CPU, it would take much longer. So if it takes very long, don't worry, it's just supposed to take that long. And I'm going to include my test dataset as my validation data here. And finally, I'm going to plot the accuracies. And in order not to waste time, I've already run the code. And basically, you can see that the result of the training, at the end of the 10,000 epochs, we got an accuracy of almost 98% for training, which is pretty good. And for the validation accuracy or the testing accuracy here, we got 95% or even 96%, considering that we have 95.9, which is pretty good. And you can see that for the accuracy curve here, we don't have a huge variance. There is a slight variance here, but it's not very huge. Maybe retuning the parameters would fix things. But basically, we have much better accuracy than our deep learning approach or our classic deep learning approach. And also, of course, shallow neural networks. So this is why CNNs are much better for the cases where we have huge data sets which happen to have multiple dimensions. And basically, this network keeps like learning for a large number of epochs, which means it has a lot to learn. So when we're having a huge data set with a large potential to learn, it's often better to use a deep learning scheme like CNNs. And basically that's it. You can run the code for yourself, and as I said, if it takes too long, don't worry. It's supposed to. And right, that's it. So in order to summarize our course, in this course, we learned the basic theory behind many famous machine learning approaches like linear regression, logistic regression, shallow neural networks, deep neural networks, and CNNs or convolutional neural networks. We now have some basic knowledge of the software tools that we need to develop our future machine learning projects. We also learned Python as a programming language. and we implemented some machine learning approaches for some robotic projects, and hopefully this course will help you design more complex machine learning applications in the future for some robotic applications. So now you understand how machine learning is quite important for the robotics society, a statement which is true for both the academic literature and the industry. So I hope that whoever watched this video and whoever manages to finish this series of videos to be a great robotics engineer one day. And you can start right now, and you can start working on yourself till you become a professional machine learning engineer. Thanks for watching, and hope to see you soon.